So, welcome everyone to this dissertation seminar. Enkeleda Balliu will present her thesis, Power Scaling of Highly Compact Single Frequency Ytterbium Doped Fiber Amplifiers. And you are most welcome here. And this is an event that is both online and on site in that sense. It's hybrid solution. So welcome everyone. We would like to introduce, we will see if we can get a picture on our opponent, Pavel Peterka. Can we get that on up for everyone to see? Good morning. Nice to have you here. Pavel is from the UFE, the Czech Academy of Sciences. Welcome to us here. I would like to say some words about the context in which Enkeleda has been working. We have had a supervisor team, me and Magnus Engholm. My name is Hans-Erik Nilsson, I'm a professor in electronics, and we have Associate Professor Magnus Engholm that has done a lot of the supervision work in the lab and so on. Magnus, can we get to see you? Or if you come here just to join us, it's easy to move. So this is Magnus. Hi everyone. So we have also an evaluation committee, which we are very pleased that will join us today and examine the thesis work. And we have Professor Magnus Karlsson from Chalmers University of Technology. I hope that you could see a picture of him somewhere. Good.
Here. Morning.
Good morning. And then we have Professor Annamaria Cucinotta from University of Parma. Very welcome.
Good morning.
Good morning. And then we have Dr. Associate Professor Andrey Koptiug that is here from the Mid-Sweden University. You're most welcome.
Thank you. Good morning.
So, I should just mention that the start seminar of Enkeleda will be broadcasted over YouTube, and then we will have a short pause to, restart for the questioning of Enkeleda by Pavel, our opponent. And after that, the evaluation committee will have a chance to ask, and then you all will have an opportunity. I'm thinking that maybe we will put in a break after the discussion between the opponent and respondent. We will see. So anyhow, it should be some time to loosen up and have a short break. We will also record the discussion, but that is only for Enkeleda's use. It will not be transmitted or used in another way. So we just would like to inform that. Finally, I would like to give the floor to Enkeleda to start to introduce. I think you have some errata as well.
Exactly.
To go through, and after that to present her work. You're most welcome. So, go ahead.
Yeah.
Use this as well. No, you have it. Oh, yes. Good.
Thank you. Thank you very much, everyone, for joining. I wanted to present the errata for the thesis work. The first one is Formula 2.1. The formula is corrected, and figure 2.6 at the legend of figure 2.6, there is a typo in the legend, and that has been corrected too. As well as page 12, section 2.2.2, there is rewritten the word pound Denver and Hall. As well a typo in page 33, where it is stated the strain applied 3 millimeter and is corrected to 3 centimeter instead. So thank you. So I'm starting. Is it shared? Not yet? Yes, exactly. So here, share screen. From a survey that I sent to laser manufacturers and laser users on what are the characteristics they would like most in a laser, I received answers such as they wanted the laser to have a good beam quality, low noise, high coherence. But the most frequent answer I received was they wanted the laser to be powerful, portable, and especially compact, which is quite in line with what we are hearing more and more today, the sustainable and development goals, especially goal number 12, the responsible consumption and production, which is about doing more and better with less, increasing the efficiency and the resource efficiency, and promoting sustainable lifestyle. Sustainability can be a positive side effect of compactness. Moreover, compactness can enable application that we thought were not possible before. This is because compactness positively impacts portability and mobility. Allowing, in this way, the incorporation of laser into LiDAR or even into cars, making possible self-driving cars, and decreasing the size of many devices, increasing the portability in many applications, such as augmented reality. Hi, I am Enkeleda Balliu, and today I'm going to present my research on power scaling of highly compact single-frequency YB-Dub fiber amplifiers. I will start by introducing you to some key concepts on laser and laser amplification, and then I will present the research question and the results related to each of them. In the end of my talk, I will conclude and present to you some future work ideas. So basically what I'm going to talk in this presentation is light and matter interaction. And we all know that matter is composed by atoms that has a nucleus and electrons that goes around it that are situated in different energy levels. But when light and matter interacts, then there are some mechanisms that are very important to understand, such as absorption. When a light excites an atoms, and the electrons that are situated in the lower level energy get excited and go to the upper level energy. But spontaneously can happen the opposite. When an atom that is excited, the electrons on the upper level energy can fall to the lower level energy, emitting an output photon that goes in a random direction. Stimulated emission instead is when an already excited electrons get excited from a photon, and as a result it will emit a second photon that is identical copy of the first. So one input photon in the input and two output photons at the output that are exactly identical copies of each other. And when this process of stimulated emission get amplified, then we have a cascade of all those output photons. And that's what is laser about, light amplification by stimulated emission of radiation. Lasers can be classified depending on their output power. Just to give you some number, the laser pointer, green one, has an output power from 1 to 5 milliwatts. They can be divided with respect to their electromagnetic spectrum, where laser covers the range from ultraviolet to far infrared, and they can be classified depending on what they are lined with. Here is depicted in this graph the line width of LED that we use in our daily life and of the laser. In this presentation, in the results I'm going to present you today, I'm going to talk about output power that are in the order of 600 to 20,000 higher than a laser pointer, and talk about laser sources that operates and emit light in the near infrared invisible range. And I will talk about laser that has a very narrow line width, the so-called single frequency lasers. Even though I mentioned that the output power I'm going to talk about are at least 600 times higher, then for some application that can still be considered low power. Therefore, the amplification of the light from the laser is crucial, because the increase of the output power from the laser means improving the performance of many applications, such as in LiDAR or spectroscopy. And as I said, it is crucial to amplify the light from the laser. In my research, I have used a master oscillator power amplifier as an amplification structure. And more specifically, the laser has been provided by Hübner Photonics, and the amplification medium is a double-clad highly doped YB doped fibers. In reality, this is a simplified schematic. But in reality it looks more like this, or even more complicated than this, where many other components take place into the amplification process. So the first research question is related to compactness. How compact, inefficient laser amplifier structure can be? And if we think about compact form design, then it needs to have as few components as possible with no additional of electronics, and to use a short fiber length that can be coiled or assembled in the smallest volume possible. So therefore, the need to use optical fiber with core diameter from 10 to 20 micrometer. And in a fiber amplifier, the minimum number of components is 5. It needs to have a signal laser, a SID, an optical isolator that protects the laser from the back reflection, an optical combiner that combines the light of the signal on the pump, and the pump diodes that pump the optical medium, and the optical medium, a YB doped fiber. So the most complex structure then, of course, is need to be developed in only one amplification stage. As a result of this research, it was possible to assemble the fiber amplifier in a volume, as you can see here, where in this picture it is depicted one of the design of the fiber amplifier. And it shows power performance that are comparable with the state of art, but it excels in compactness because it is developed only one amplification stage and use active fibers that are nearly 1 meter or less than 1 meter long, for a total amplification stage volume of 600 centimeter cubic. But what happened when single frequency light propagates into relatively small core fibers, such as 10-20 micrometer? Then stimulated Brillouin scattering generates. And what is stimulated Brillouin scattering? Stimulated Brillouin scattering is a nonlinear interaction of the light with the optical medium. What happens is that when the pump propagates into the fiber, then due to thermoelastic motions of the molecules in the active medium, then part of this power propagates in the backward direction, forming the Stokes wave, which will superimpose with the pump wave and create bit signals, high intensity signals that will modulate the optical medium in a periodical way, creating acting such as a break grating that is moving. So when the break conditions are fulfilled, then more and more part of this pump light will be back reflected in the backward direction. Then stimulated Brillouin from spontaneous will be transformed to stimulated. And so the stimulated will exponentially amplified on the backward direction. The pump power will not anymore positively contribute to the amplification of the signal, which will be a power scaling limitation as well as very harmful for the laser itself. So it is very important to suppress SBS. So how efficiently can SBS be mitigated using techniques compatible to the compact form? To address, there has been many mitigation techniques to suppress SBS, a group of them that concentrate on broadening the Brillouin gain bandwidth, and some of them that broaden the laser line width. In this research, I'm going to present the investigation of the strain distribution technique in the use of highly doped fibers. This is because the other group that is concentrated on the broadening of the laser fiber requires additional electronic and therefore not compatible to the compact format. To address this research question, then I have investigated the implementation of a tensile strain on the active fiber, as well as the use of the highly YB dope, both in the phosphate host and silica host. So, first of all, how efficiently can SBS be mitigated by using the tensile strain? On the left, in this slide, you will see a photograph from the laboratory when the strain was applied to the active fiber, and on the right you will see a schematic of the applied strain. The strain is determined in percentage, and in this case you will see a 5-segment strain where the segmentation length was determined using the patent by Jablon et al. And the strain will be higher in the beginning of the fiber, lower in the beginning of the fiber, and will increase with increasing of the fiber length. And this is because in this case the fiber amplifier was pumped in the forward direction. So by using forward pumping, when the signal of the pump propagates in the same direction, and as you can see here in this graph, that is the simulation of the propagation of the pump and the signal using a commercial software, RPi-Photonics, you will see that the signal propagates amplified, and it will reach its maximum at the end of the fiber, and so will the stimulated Brillouin scattering. Therefore, the maximum amount of strain is applied at the end of the fiber. But in order to understand why SBS change or is suppressed by strain, then I investigate the spectral characteristics of the Brillouin scattering. Here you will see, here it is depicted the Brillouin gain spectra of a fiber that has a core cladding diameter of 7 to 125 micrometer. And the fiber has been strained in 2 points with a uniform strain. In this graph you see 2 peaks. The first Brillouin gain peak is related to the measurement system, and it has in itself a fiber amplifier, and the second peak is related to the fiber under test. This is the case where no strain was applied to the fiber. And when the strain is applied to the fiber, we will see that this peak will shift to the right, showing that by applying a strain, then the central Brillouin frequency will shift, and therefore by applying a non-uniform strain, each segment will have a different central Brillouin frequency. Doing so difficult the amplification of the Brillouin scattering in the consecutive segment. Here is the result when using a 0.27% strain, and the Brillouin peak was possible to shift by 0.27 gigahertz for a total of nearly 1 gigahertz per percentage strain. In the case of a fiber amplifier, the fiber amplifier, as I mentioned, was forward pumped, and the laser was operating to pulse mode, which give another possibility to detect onset of the SBS, since when the SBS start to be manifested, that it will be visible also in the output pulse, since the output pulse will start to deform. By applying strain on a 42 centimeter fiber, we will see that here you see the graph of the output peak power with respect to the lunge pump power, and when no strain was applied, a maximum of peak power of nearly 1.7 kilowatts was able to be achieved. And when strain was applied in it, then the output peak power increased by 5 times. So showing the feasibility of this technique, then it has some advantages because it does not need the additional of components or electronics, and improve and increase and successfully suppress SBS by nearly 8 dB. But on the other side, it is not so straightforward to apply strain into a fiber while coiling, and it is challenging to control the strain as the strain is not conserved with time. Therefore, it was investigated another SBS mitigation technique, the use of highly wide-beam fibers. Why? Because as we can see here in this formula, then the SBS power threshold is dependent on both the area of the fiber and the fiber length. So the optimal case will be to use a short fiber with a small core diameter fiber. So therefore has been investigated the use of wide-beam phosphate fiber and silica fibers. To address the first case of the highly wide-beam fibers, then the use of YB-Dov phosphate fibers. Then first and foremost, why a YB-Dov phosphate fiber? Because the phosphate host allows a larger amount of the earth ions without clustering and exhibit much weaker photodarting loss. And the most important is that the SBS gain coefficient is 50% lower than that of the silica host. But this comes with some challenging, because the glass transition temperature of the phosphate fiber is nearly 500 degrees Celsius, with respect to the silica that is 1000 degrees Celsius, making challenging the integration of the phosphate components with the silica ones. It has higher background losses, nearly 1 dB per meter, and lower absorption and emission cross-section than in the silica, in a factor of 1.5. So, from a collaboration with Polytechnic of Turin, it was possible to they provide us the YB-Dov phosphate fiber. In the left, you will see a scanning electron microscopy of the fiber, which has core clad in diameter of 20 to 176 micrometer. And in the middle, you will see the splicing figure image, the splicing of the phosphate fiber with the silica ones. The fiber amplifier was forward pumped and was operating in pulse mode. The performance of the phosphate fiber was compared with the silica one, where different fiber lengths were used. 30, 40 and 50 centimeter of the YB-Dov silica fiber were used, and it was possible to achieve a maximum peak power of 6.5 kilowatts with no sign of SBS by using 40 centimeter of this YB-Dov silica fiber. And when using YB-Dov phosphate fiber, then it was possible to achieve a maximum peak power of 11.7 kilowatts by using only half of the fiber length as in silica, so namely 20 centimeter YB-Dov fiber length. And that made possible to increase the SBS power threshold by 3 dB. In both those cases where the tensile strain was applied and the use of the YB-Dov phosphate fiber, then this SBS was successfully suppressed by 8 dB and 3 dB respectively, and the fiber amplifier was operating in pulse mode, which means that by suppressing the SBS was possible to improve the performance of the fiber amplifier and therefore increase the performance in applications such as LiDAR or spectroscopy, coherence spectroscopy. Another mitigation technique was used, namely the use of a highly YB-Dov silica fibers. In this case, the fiber amplifier was operating in continuous mode, and both forward and backward pumping scheme were investigating. In this case, shown in the slide, the forward pumping scheme is demonstrated, where three different optical fibers were used. It was investigated fibers with one fiber with a core diameter of 10 micrometer and two with a larger core diameter of 15 micrometer, where one is commercially available with the highest YB-Dov content, and the fiber one is a custom-made, highly doped YB-Dov fibers. In terms of output power, then when using a fiber with a 10 micrometer core, it was possible to achieve a maximum output power of 48.3 watts, and then afterwards, then the output power was limited by SBS. When increasing the core diameter from 10 to 15 micrometer using the commercial YB-Dov fiber, then the output power, as it is shown in this graph, was possible to be increased to 74 watts, increasing the SBS threshold by 1.7 times. And when using the highly doped custom-made YB fiber, the output power was increased to 82 watts, for a total increase of the SBS threshold of 2.3 dB. So when using a backward pumping scheme, the same YB-Dov fibers were investigated the difference in with respect to the forward pumping scheme, as we can see here in this graph, is that in the backward pumping scheme the population inversion is more uniform and therefore less problematic for other power limitations such as photo darkening. In terms of output power, as you can see here, SBS is more pronounced because of the backward propagating pumping. Then even the passive optical fibers will contribute to the total SBS. And it was possible when used to achieve an output power of 33 watts when using a 10 micrometer fiber. And by increasing the core diameter to 15 micrometer, then the output power was increased to nearly 58 watts, and the output power in this case was limited by SBS. When using only 1 meter of the highly YB doped custom-made fiber, then the output power was the maximum output power achieved was possible to be 81.5 watts, and this power level were not limited by SBS but by the available pump power. So by increasing the SBS power threshold by 2.5 times by using the highly YB doped fiber, then it was possible so to improve and would need to be then it's useful for other applications such as augmented reality or frequency conversion. But the use of highly YB doped fibers and very short fiber lengths will increase the thermal load generation of the YB doped fiber. Therefore, it is important to investigate the thermal loads in the active fiber. The major source of the heat in the fiber is quantum effect, that is the difference in energy of the pump and the signal. Where in our case, in this investigation, since we used the pump wavelength of 976 nanometer and a signal wavelength of 1064 nanometer, then the quantum effect was nearly 8%, meaning that from the total pump power, then 8% of it will be transformed into heat. So how efficiently can SBS be mitigated using, can thermal limitation be reduced compactly? Then to address this research question, it was investigated the power limitation due to thermal load generation and investigate techniques that can reduce the thermal load generation and extract heat from the fiber, such in the case of anti-Stokes fluorescence cooling. So in nearly all the optical fiber that has been investigated, they are double-clad optical fibers, where the core and the first cladding is made of glass, and the second cladding is a polymer cladding, meaning that its long lifetime operation is ensured only if the temperature is nearly 80 degrees Celsius or below it. Therefore, it is crucial to optimize the cooling of the optical fiber. To optimize the cooling in our investigation, the cooling of the optical fiber in our investigation, the fiber was coiled in a U-grooved mandrel, and the outer part of the fiber was covered by a copper tape to increase, as I mentioned, the cooling of the fiber. And it was very important, crucial to investigate where the heat load generation would be a power limitation for a power scaling limitation. And to do that, I investigated the difference in or the temperature increase of the coating for the 3 YB doped fibers investigated. And it was shown that for the highly YB doped custom-made fiber, then the output power would have been limited when the pump power would reach a power level 200 watts. Knowing that the slope efficiency for this fiber was demonstrated nearly 75%, then the output power would have been in the order of 150 watts. So therefore it was crucial to investigate techniques that will reduce the generation of the thermal loads in the fiber. And therefore the fiber amplifier was operated in quasi-continuous mode, where the pump was modulated with a duty cycle of 1%, and that made possible that the maximum current used for the pump diode was double of the manufacturer current continuous rating, and by doing so was possible to enable and to extract twice as much power from the pump diode. This reduced the thermal load in the pump diode, but not only in the pump diode, also in the active fiber and in the nonlinear crystal when the fiber amplifier was used as a source for second harmonic generation. So here is the graph that demonstrates the extraction of the output power twice as much in the case of quasi-continuous wave mode operation with respect to the continuous one, and making so that the performance of the fiber amplifier were possible to be investigated further. In the continuous mode, as you can see in the graph on the left, where the output power is presented with respect to the lunge pump power, then two fiber lengths were possible to be investigated, 3 meter and 1.5 meter. And in the case of 3 meter YB-DOV fiber length, then the output power was limited by SBS. While reducing the fiber length to 1.5, then the limitation was the available pump power. But by operating it in quasi-continuous mode, then was extracted double as much as pump power, so the performance of the fiber amplifier in the case of 1.5 meters were possible to be further investigated up to the onset of the SBS for an output peak power of nearly 42 watts. So therefore, I investigated further the cooling, some compact method to cool the fiber by investigating anti-Stokes fluorescent cooling. I had the possibility to be part of a research conducted from Professor Michel Digonnet group at Stanford University, where I theoretically investigated the anti-Stokes fluorescence cooling efficiency for different ion host combination. But what is anti-Stokes fluorescence cooling? Anti-Stokes fluorescence coolings happen when the pump wavelength is longer than the anti-Stokes fluorescence wave, means fluorescence wavelength. And therefore, the energy of the pump photon will be lower than the means fluorescence energy, so that when the fluorescence will be emit, will be extract heat from the fiber instead of emitting or giving heat to the optical fiber. So anti-Stokes fluorescence cooling depends on many parameters, such as the pump energy, spectral width of the rare earth transition, concentration quenching, absorptive loss, as well as absorption and emission cross-section. Therefore, it is crucial to find the best ion host combination. And to do this, on the left you will see the efficiency or the heat extraction per unit length. The maximum heat extraction per unit length, as I said, it depends on many parameters. And here on the right, I present the results related to the YB ion, since the rest of the research is related to YB ion. And it shows that in the case of YB ions, the best host combination would be phosphate ones. I need to highlight that this was a theoretical and numerical calculation study. So the next research questions, which is more an extension of the first research question, so how efficiently can the near-infrared fiber amplifier be converted to the visible range? And to do that, it was used the most simple and compact schematic configuration with a single pass, external cavity, single pass, single crystal, of second harmonic generation. And to investigate the second harmonic generation efficiency, different nonlinear crystals were investigated. In terms of output power, then both the pulse mode operation and the continuous mode operation were converted from 1 micron, so from near infrared to green light. And it was possible to achieve an output peak power in the order of 1.5 kilowatts when nanosecond pulses was generated when investigating a 10 millimeter KTP crystal. 7 kilowatts output peak power was achieved when the pulse width were in the microsecond order, and 3.5 watts was possible to be achieved in a 5 millimeter pp-ln when the fiber amplifier was operated in continuous mode. So to conclude this talk, I demonstrated that it is possible to efficiently suppress SBS in a compact way, and where using a YB-DOF fibers resulted the most feasible choice. I demonstrated also that it is possible to achieve high performance in only one amplification stage for a single frequency fiber amplifier, both in continuous mode operation and pulse mode operation. And as a result of this research was successfully demonstrated the most compact fiber amplifier demonstrated so far for this kind of laser, namely for a volume of the fiber amplifier of 600 centimeter cubic compared to the state of the art. And I demonstrated different compact way to reduce the heat generation in the fiber and extract heat from the fiber. But among further investigation can be still interesting to conduce. It can be very interesting investigation to continue investigating the performance of fiber amplifier with an improved version of the YB-DOF phosphate fiber, as well as to investigate the spectral characteristics, the brilliant spectral characteristic of this fiber, and to integrate other compact SBS mitigation technique to the already investigated ones, such as thermal gradient technique, as well as the use of the tapered fiber. So with that, I would like to thank you for your attention, and you're welcome for questions.
Thank you, Enkeleda. And this ends the first part of the dissertation, the seminar, meaning that we will shut down the YouTube channel and go over to only Zoom. And we should have a short break as well before to just do this change. So we will take about 10 minutes break. And then after that, I would welcome opponent, Associate Professor Pavel Peterka, to enter the floor together with Enkeleda to discuss the thesis, questions and so on. So, a short break.
Thank you, everyone.